What you call informal.
Yeah. It's informal. Yes, you all the students. You are all young students and some professors, but most of them students.
Fine.
So good morning, everybody. As you know, when we have people of the status of Dudley Herschbach, that in addition to be a great scientist and a great person, is a very good friend of us, and we love to have him here at the Donostia International Physics Center. We used to have an informal meeting, mainly with young students. One of my students already has prepared the question, because I always and then about his life, why, whatever you want him to ask. So I will not introduce him. He is a Nobel Prize for Physics, professor of Harvard. In addition to that, his most important achievement, as he himself has declared many times, as my two daughters really admire more, is that he appears in The Simpsons. 14 seconds of glory were worth, in your own words, more than a whole career in science. But we want to hear both also about The Simpsons, but about science. He gave a fantastic talk yesterday, full of humor, brilliant, and with a deep content. As I am very grateful, he is a very generous man. When I told him we are going to make you work because we want you to give the talk, to advise me on and our team in the endeavor of the Donostia International Physics Center, to visit Nanogune, to have a meeting with Jackie Unde, the Academy of Science, Arts and Letters, and in addition, the students will love to talk to you. He said, almost, your wishes are my command. So we are very happy, very grateful, and very honored to have you here, sir. And the floor is you. If you want to talk 5 minutes about your life, or you want, everybody knows you, but it will be a nice summary of 5 minutes, and then we open the floor for questions, if it's okay for you, okay?
Of course.
So thank you very much.
I'm happy. Your wish is my command. Yeah, right. But I know from an interview with a reporter yesterday that people like to know from the beginning how I got interested in science. And so I grew up in what was then a very rural part of California with all fruit orchards. I milked cows. We had pigs, chickens, a little farm and all. My family didn't even know anyone who had graduated from college, so I didn't expect to go to college. I didn't have any friends who expected to go to college. That's how it was. It's hard to imagine now because so many kids expect from the beginning to go to college, but it wasn't the case then. But what really got me aware of science was when I was about 10 years old, we happened to visit our grandmother, which I always enjoyed doing for many reasons, but one was she had National Geographic magazine, which you know still today has wonderful photographs visiting exotic places and all. But this had an article called The Heavens Above by Donald H. Menzel of Harvard College Observatory. Well, of course, I paid no attention to Harvard College, but it must be the first time I ever heard of Harvard. But this article had beautiful star maps, gorgeous star maps of the constellations with mythological figures superposed. And I was intrigued with those. So my grandmother saw how much I liked it. She gave me that issue of National Geographic. I still have it. But I began reading about astronomy. I made my own little star maps. I would trace them and then make pinpricks so I could climb up a tree in the backyard for my private observatory. But since I didn't want to adapt my eyes to light, I hold up the sheet with the pinpricks and quickly click the flashlight to see the pattern and then find it and so on. But this was my first encounter with science, and when I got to high school, I found of course, much more about it, especially mathematics, which I loved right away. But to give you an idea what the high school was like, well, I should mention my grammar school first. It was 4 rooms, 80 students in the whole class. So 2 classes per room. we had only a little bookcase about this big, some books. One of them was about the planets, though. But then we got to high school, again, it was small. They had to bus people 25 miles or so to have enough for this high school. This is in what later became Silicon Valley. I visited my high school 15 years later and found that in that same school district there were now 13 grammar schools, all 500 or more students, compared with the 80 in one. And there were 5 high schools, all 5 times bigger than mine, and so on. But the first class in high school, in walks the teacher. It was about the algebra, and he said, "I don't know much about algebra." The next thing he said, "However, I can tell you one thing. In this course, if you calculate by the right method but get the wrong result, you get no credit." Because, as he explained, he'd just come from the Second World War, where he was in the artillery corps, and he said, if we calculated by the right method but wound up shelling our own troops, we got no credit. That made a big impression. But the result was, as I look back years later, that the students became very resourceful. And within 2 or 3 weeks, there were, in this small class of 20, 2 or 3 students who had a better understanding of algebra than Mr. Drummond, our teacher. But that didn't bother him. He was from the Army. He understood his responsibility was to make sure the privates and corporals did things up to regulations. So he encouraged the students to explain to him, and therefore the other students, what they thought they understood about algebra. And it was the same way until my 3rd year in chemistry. We had a fantastic teacher, a master's degree from Berkeley in chemistry, wonderful. And that's really why I wound up becoming a chemist. When I went on to Stanford as an undergraduate, about halfway through high school, my coaches had been telling me, "Oh, you have to go to college," because I was a good football player. And I was a good student too, so my teachers would say the same. And then I applied to Stanford and was accepted. I actually got telegrams from many other colleges, from football coaches, congratulating me on being accepted, even though I hadn't even applied to those colleges. At any rate, I soon found, because I must have put down chemistry as a possible major, I was assigned to as an advisor, a young assistant professor of chemistry, who turned out to be my second really important mentor after my high school teacher. And he had a huge effect on my development as a scientist. Key thing was, after my 2nd year, he invited me to be a research assistant in his lab during the summer. And so I heard graduate students talking a lot about quantum mechanics, whatever that was, and clearly involved probabilities a lot. So I decided maybe I should take a course in probability theory. So I look in the catalog. There's someone named Polya. I didn't know this, but he was a very famous mathematician, and especially in probability theory, but also in the teaching of mathematics. So I took the course from Polya. I absolutely fell in love with him. He was Hungarian and enchanting teacher, very famous. So I took every course after that he taught, including, for example, a course, Higher Mathematics from Lower Point of View, and next semester, Lower Mathematics from Higher Point of View. So I always tried to emulate Polya's style. But soon I made the generalization that anything taught by a Hungarian mathematician I wanted to take. Well, there were 2 or 3 other Hungarians in the Stanford math department. So pretty sure soon I was taking not only everything that I could from Hungarians, but all mathematicians. So inadvertently, I completed a major in mathematics while also doing so in chemistry and mostly physics, because I was so excited about all of it. But Stanford in those days only allowed you to major in one thing, so I decided I'd officially major in math, even though I knew I wanted to go on to graduate study in chemistry and all. I had partly the wrong idea I thought that mathematicians spent their time all by themselves proving theorems. And I knew I didn't enjoy that. That wasn't the part of mathematics I enjoyed. I was a more social person, and I knew chemistry was very social. Why? Because we spent hours in labs. And there, the labs, as I try to explain to students, many students don't like the idea of labs. I say, what do you mean? That's the most social opportunity you can have. You can wander around and talk to people. Whereas a lecture hall, you're stuck in chairs. It's not very nice and all that. But so then I did go on to graduate study at Harvard. I was actually in the physics department my first year because I wanted to do chemical physics, and they didn't offer a master's degree in chemical physics. It was a committee between chemistry or physics. So you would start either in chemistry or physics. And the result was I had a wonderful year. I met many fantastic people. 5 of the teachers that I had in physics either had or got the Nobel Prize at Harvard. And then in chemistry, that year, Peter Debye was visiting and gave an absolutely fantastic course. It was called Introduction to Chemical Physics, but it could have been my life work. And I don't know how many of you know the saga of Peter Debye, but who was a fascinating person, did many different kinds of things in theoretical chemistry and physics. So there's tremendous stimulation and fostering great experience interacting with other graduate students. Part of the time I was a graduate student, I got to work in Canada at the National Research Laboratory because it turned out in my work I needed to have higher resolution. I was doing microwave spectroscopy than the Harvard instrument had. And so I worked in the National Research Council in Ottawa for 2-3 month periods. And that was the time Herschbach was running the lab. And it was wonderful to go to tea every day and hear him telling great stories about the development of molecular orbital theory, molecular spectroscopy, and all of this. So you see, I had a very, very lucky time, partly because I did not get deflected by the fact that after I quit football my first year, I got an invitation to try out for the Los Angeles Rams professional team. Now, I was very lucky because today, someone in the same situation would almost have to accept, because even a rookie football player gets millions of dollars a year. That wasn't true back then, fortunately. So it wasn't such a great seduction. So I'm very happy with what I got started up. I should just say a little bit about how the line of work that I'm best known for got started. My last year at Stanford, I had a course on Walter Meyerhoff. I mention his name specifically because I later learned that he and his family had fled from Frankfurt when the Nazis came to power. And Frankfurt, of course, is where Otto Stern, as I mentioned last night, did the Stern-Gerlach experiment. And there was this connection. But it turned out that Meyerhoff, in a class I took from him, in a sort of digression, said a little bit about Otto Stern. And that's why I first heard of molecular rays and all, that I immediately said, gee, that's the way we should do chemistry. Because from my undergraduate advisor, Harold Johnston, I had learned that to understand what happened in chemical reactions was a terrible mess. There were usually a lot of steps, and the means of unraveling the steps were very primitive because you had all these things going on at once in ordinary conditions of chemistry, whether it was gas phase or liquid phase. You had no way of sorting them out. But with the molecular beam thing, you could see, gee, if you collided two beams, they only have a chance of one collision. And then if you can detect the product right after it's formed, you can do a kind of physics. It was really physics of chemical reactions at the molecular level and single collisions. And of course, I spoke with my advisor about it, and he laughed and said, yes, of course. but not enough intensity. That's what everyone thought. They thought it was impossible. But I did some calculations, and I convinced myself that, yes, you could do it for at least one family of reactions. Alkali atoms love to give an electron to some electrophilic molecule that will accept it, and then they'll extract, say, especially if it has a halogen atom, to make a salt. And Michael Polanyi, the father of John Polanyi, who I later knew very well, had in the 20s done primitive experiments where he had a tube this long filled with argon, diffuse an alkali metal like sodium in one end, concentration gradient goes down, diffuse a halogen containing molecule like chlorine, the other end, diffuse gradient goes down. In the middle, where you have the biggest joint concentration, you get a salt deposit. But because even then in the 20s they knew pretty well what the diffusion rate would be, they could determine from the width of the salt deposit how fast the chemical reaction occurred. Beautiful. And he could vary the halogen-containing molecule that he diffused in, and he got the first evidence for how chemical structures affected the rate at which a reaction occurred. So it turned out those reactions were the ones we could first study, and people weren't too interested because they thought there's such a special family of reactions. They won't really teach you anything fundamental about chemistry. Well, what happened was, because the alkalides love to transfer an electron, it came to be called the harpooning reaction. Electron jumps from the alkali to the target molecule, and then the Coulomb force attracts them together. That we, before long, were able to find out, my students and I, many modes of reaction and relate it to the electronic structure that was determined by the orbital of the target molecule that accepted the electron. Well, a few years later, a brilliant postdoc, Yuan Li, joined my lab, and we were then able to build, under his leadership, a wonderful mass spectrometer detector that was so sensitive we could actually detect the product equivalent to 1 molecule per cc. That's very small, right? But 1 molecule in this little volume here. And with that, we could expand over a wide range, study all sorts of reactions. We weren't limited anymore to alkali. The beautiful message is, what we had learned about how electronic structure governed what happened, the dynamics in the reaction, how much energy is released from breaking bonds into translation, into rotation, into vibration of the products, the directions they go, the angular momentum they carry, all these things that reveal how the forces operated in governing the reaction. It turned out that we could understand the reaction that did not involve electron transfer. It's in the same kind of terms. So the limited family of alkali reactions we started with actually had taught us much more about chemistry in general than we could have known until we developed a wider scope of experiments that allowed us to find that out. But really, the beginning thing was more universal than we could have imagined. So that's the short version. There's lots more details that are fun to talk about, but I never imagined how this would work so well. In the early days, people referred to it as the lunatic fringe of physical chemistry, and it seemed that way. I was urged not to do this. It was too scary. It was too unlikely to succeed, so I wouldn't get promoted as assistant professor. And I felt then and said, I don't care. I have to do this. It just appeals to me so much. So I mention all that to you because if you happen to be as lucky as I and find yourself in that situation, don't hesitate to do the thing you most want to do, because you may not have that chance again. And another thing that was terribly important that I never anticipated was the fact that it was doing something brash, something really unusual, something lunatic fringe, attracted to me right away the most wild, interesting, ambitious students. They weren't satisfied to do the safe sort of thing that most people were doing to get a PhD in chemistry in those days, some sort of spectroscopy typically. So that, of course, made the whole thing work, and also brought to me the greatest satisfaction of all, which has been the working with other people and these adventures, as you rightly term them. And it's been a lovely thing. So,
thank you very much. So now there are seats here for the ones who are there standing up. So. And then questions, comments. So the adventure can be crazy, but the adventurer has to be trusted.
Well,
the leader of the adventure.
Nature deserves a lot of credit. I mean, nature was kind. Still is, I believe it. She's willing to tell you fascinating things if you are persistent. And,
first question, I told.
Actually, I have Dr. I know I respect.
He's designated for the first question? Was that it?
He's expected to be asked, but
Good.
he insisted in not preparing questions.
That's okay.
So, but now you were telling about... Hola? Yeah? Okay. So you were telling about your life, and so I've seen that you have been living all around the States in the best labs in the world. So if you had to choose one city, one lab to work now, after all these years, which one is the most...
Well, right now, I think this city is a very nice place to work.
I expected an answer like that.
I've only had a chance in recent years to discover it, but my wife and I both are fascinated and delighted with our experience here. And this institute is wonderful. I mean, look at the variety of people from all over the world, ideas, many different levels of things going on here. It's an exciting place. So I'm actually hoping to come and live here for a while, not too long at first, but maybe more and more.
We are negotiating with him, the details, not if, but when he will be coming with a sabbatical in Nickelback. He has already accepted, and we have to talk to our friends in Nickelback for the details, but the question is when and not if. So we are very happy with that.
I know Professor Lucas has had a nice time. I forgot to speak to him briefly about it, but I met him here at the Einstein Fest 4 years ago, and he gave a wonderful talk, and it's a very admirable booklet. It's astounding how much in one lecture, it's just still hard to believe, but that I've actually used in the freshman seminar course I teach at Harvard. So
which lab in the United States you will choose?
Oh, in the United States? Well, I had a great experience in 4 years at Berkeley. After I got my PhD at Harvard, I went right away to Berkeley, and that's where I started this molecular beam work. Then when Harvard invited me to come back on the faculty, it was a very, very difficult decision because I was a third-generation native of California, and I felt very, very much at home there. I loved Berkeley for many reasons, but I had such a great experience as a graduate student at Harvard that it was very hard to decide. And I actually would wake up at night for the next 2 or 3 months, even weeping, because it was so hard to decide. I didn't want to leave Berkeley, but I had this chance to go to Harvard. And then one day I realized that some internal person had resolved this. I think probably all important decisions in life are made in the right side of the brain or something, wherever, you're not sure. And so I went back to Harvard, and that's been, of course, a very happy home, too. I had liked New England from the time I had been a graduate student. So I would have to say I'd be as happy as possible, either Berkeley or Harvard, because I've been at both places. Stanford is another place. More recently, I've had the opportunity to visit 4 weeks a year in the physics department at Texas A&M University, which I also found surprisingly much more interesting than I expected from what people had told me. Again, it's a place that has wonderful people doing fine work, and from all over the world. I mean, where else would I meet physicists from Mongolia? I mean, but Mongolia, I found out, has lots more interesting physics going on than I ever would have imagined. So that's the beauty of it. Everywhere you can go. You know, Hemingway wrote a famous book, A Movable Feast, which he talked about his Paris years, and then about how as you go around the world, you can take this with you when you away. So that's the way it is with science especially. Everywhere you go, you have sort of an automatic passport because you're a scientist. There are scientists you meet, and you're interested even if you've not known one another personally before. But if you said, you know, for home base, I would certainly be happy with any of the places I mentioned.
Okay, no questions? It takes a little bit always to warm up, but later it will be difficult to stop.
Good, good.
I'm sorry.
Oh, good.
I'm interested in serendipity. They told me that it helps to science researches. How arrives science research? How arrives el descubrimiento científico?
How you reach
Pedro
the
Miguel.
scientific discovery.
And
How it comes, the moment of discovery.
Yes.
And how about serendipity?
Serendipity.
Serendipity, which is a very elegant word for luck. Right. Well, I think one important ingredient is optimism. A very outstanding scientist, Langmuir, used to say that the people he wanted to recruit to his laboratory, his first criterion was optimism, because an optimistic person will try things that may turn out to work, whereas someone very smart and all knows so much, it's not going to work. So if they're pessimistically inclined, they won't try it. And you can see that it clearly is an advantage. There's also risk. I mean, optimism mean you gamble all your money away right away because you expect to win something that is not plausible. But if optimism is tempered with some willingness to think and learn what you can, to plan carefully before, then it can turn out to be lucky. Partly luck grows from careful preparation. They often say that in many sports events, it's in the practice field that the game is won because you prepared yourself really well. My PhD, I mentioned, was in microwave spectroscopy, and that turned out to be perfect preparation for what I did later, because in microwave spectroscopy, some of you may know, especially as done by chemists, you likely want to work on a fairly large molecule that has what we call different moments of inertia. So the spectrum is very complicated. You have thousands of lines, and there's no chance of assigning their quantum numbers until you estimate carefully from what you can guess about the structure of the molecule, what these moments of inertia are, and you find certain lines that have the right kind of Stark effect when you turn on an electric field and the lines split and all. And when you finally identify three, then you have 3 moments of inertia. And so first approximation, if you treat it as a rigid body, you can then predict many other lines and then you evaluate some more constants that are correct for vibration and distortion of the molecule and so on. So you learn careful planning, take all the information you can, and then you can unravel this incredible, complicated spectrum. So then when we began planning to do molecular beam experiments with reactions, you can calculate a lot. From how much product yield you need, what sensitivity, all the rest. And so it was this doing it the way a spectroscopist would, where some other people who went in the field didn't do that, meant that we got the key parts right. If you get the most important things right. Otherwise, you can spend a huge amount of effort unproductively on things that don't work experimentally. So that was part of the luck. But optimism combined with careful preparation and an urge to try to do something that will change people's opportunity to understand basic phenomena, like example was chemical reactions at the molecular level. That, I think, is a nice combination, and I recommend it to you. I mean, the one way to get at it is read lots of papers in the literature, and you'll be stimulated. So often in science, it's a matter of you get an idea in this area, and from reading something interesting or hearing a seminar, as I described with Otto Stern last night, and then you read one over here, and you say, "Gee, I wonder if we can put these together." That sort of thing. So there are lots of combinations that you can find that way, and then you will find what appeals to you, sort of intuitively, maybe emotionally. That's worth exploring to decide whether that's what you want to pursue.
Okay, I will ask you a question because interpreting the wish of the audience.
You can tell from the expressions.
I can see in the faces what they want to know. But
right.
One feeling I'm sure all of you have, because it's not an unusual feeling, is that you are in a time in which almost every interesting thing is already discovered. And Professor Herschbach or Dudley said yesterday that is not the case. In fact, this feeling is shared by many people. I was reading the other day the preface of Einstein to the Optic of Newton, and he writes there, what happy moments on the childhood of science when everything was to be discovered. Okay. Reading about quantum chromodynamics, one sees that Feynman says, happy moments, this more or less this bloody Schrödinger just writing an easy equation and solving it for an easy case, the Schrödinger atom, and gets the Nobel Prize. No? So it is this sentence in the Spanish literature, cualquier tiempo pasado fue mejor, ¿no? Las manriqueñas, ¿no? Recuerde el alma dormida, aprendíamos en la escuela, vive el seso y despierte contemplando cómo se pasa la vida, cómo se viene la muerte tan callando, cuán presto se va el placer, cómo después de acordado da dolor, como a nuestro parecer cualquier tiempo pasado fue mejor. So we all think that the past was wonderful because with little effort you could get marvelous achievement. And it was fascinating for me to see exactly this idea better and more beautifully explained by Dudley yesterday, encouraging the students that you have an infinite sea of possibilities in front of you, and cualquier tiempo pasado no fue mejor. Every past time was worse. Can you? I'm sure I have interpreted you feeling, no?
No, what I would say is so charming about the past is often relatively primitive apparatus and even primitive approximations in theory and so on could produce such beautiful, encouraging results and all. But what I emphasize to students who have exactly this question is that it's impossible for you to appreciate the advantages you have because you inherit a legacy of tools, conceptual as well as instrumental, that the previous generation didn't have. And that really is profound. It means you actually will think differently, think differently, as well as being able to do differently than the previous one. And one favorite example I have of that is magnetic resonance imaging. Nuclear magnetic resonance is a fabulous field, starting in 1945, by the 70s and 80s, got to the point you could determine structure of proteins by magnetic resonance. You send in many pulses and all. And that became possible because you could use computers to analyze all the data, which you couldn't do in the early days. So Purcell, who I knew very well, was one of the first people to do magnetic resonance. He told me he never dreamed he could do something like that, protein. Also, he never dreamed you could do magnetic resonance imaging. Well, the fascinating thing about the magnetic imaging goes this way. For all the early work, the idea was to have the most uniform magnetic field on your molecule, so you would define very precisely the resonant frequencies, because the magnitude of the field determines how the splitting of the energy levels due to the orientation of nuclear spins, and you want to have them very well determined so you get the frequency just right. But what you want for magnetic imaging is the opposite. You want a field that is terrible in a sense, because you want it to be different at every location within your sample, so that there's a connection between the resonance, the magnitude of the field there, and the position. But people didn't even think of that until, I think, computers became so common and powerful that you could, in your thinking, whether it's quite conscious or not be inhibited by the fact that, gee, you're going to have all this data, all these different points, different frequencies. You have to put them all together to get your image. And if you've ever, any of you had, and some of you all have sooner or later, a magnetic resonant image, they put you in this big superconducting magnet on a tray, and you'll sit there and it bangs away. You think it's like somebody's pounding nails in your coffin or whatever. It's very scary. You sit in there 45 minutes. Why? Because it takes so many scans all over the place to create this three-dimensional image. And it's all put together by computer. Well, nobody thought of using a lousy field that's different all over the sample before. And I'm sure it's because the thinking became feasible when you had in the back of your mind, no problem. Having lots of different data you have to put together. So it's, I think, a nice example of how the later generation could do things that the pioneers who started out doing the original magnetic resonance didn't anticipate at all. They were very, very capable people, but it was just way over the horizon. And the same, I bet many of you are going to witness the same thing in your career. When you look back, you'll see, yeah, that's how. We hadn't anticipated these tools we have. Because, as they say, humanity are humans are tool-using creatures. And these tools, conceptual as well as instrumental, they make huge, huge difference. And so you can look forward to having lots of adventures that weren't possible for your predecessors.
Since the youngsters don't want to volunteer to speak, let me ask a question about Stern. You mentioned that you had the luck of meeting Otto Stern, and he told you this marvelous story about discovering the cigar effect,
Yes.
Somebody was overlooking over his shoulder, it was Walter Gerlach.
Yes.
Did Stern tell you anything more about Gerlach and what Gerlach became after all this wonderful experiment?
I did not discuss or hear Otto Stern discuss Gerlach, but later I did look into the history of Gerlach. So I've actually written an article, or in fact 2 or 3 articles related to that. So I know, the Stern-Gerlach experiment involves splitting the beam of silver atoms. And I showed last night this sculpture in Frankfurt before the new Experimental Physics Institute that has a picture of the magnet that split the beams, and then a portrait of Stern on one side, Gerlach on the other. And as Professor Lucas is, I think, alluding to, when you see the beams split, it also reminds you of this experiment they did together in 1922, what happened after 1933 when the Nazis came to power. Stern, being Jewish, left Germany. Gerlach, who was very loyal to German, stayed, and even though he never himself became a Nazi, and in fact he personally objected to attacks on Jewish people and all, later in 1944, so every 11 years, he became in charge of the German atom bomb project. Heisenberg had previously been in charge. He became Heisenberg's successor. And when, after the war, 10 of the leading German scientists who had worked in that area were immediately rounded up, and they're taken to Britain, to a place called Farm Hill, and they had bugged the place so they could record their conversations. We learned a lot more, but Gerlach, it seemed, was very upset when he learned that the Americans had developed the atom bomb and felt he had failed the fatherland and all the rest. Later, however, he worked hard to try to limit the atom bomb arms race that developed and so on. They met only once later, and they met in Zurich, because Stern never went back to Germany. And then later, Gerlach gave a very lovely obituary speech about Stern. So I've looked into all of those things, so I can tell you more if you like.
Unusually quiet.
They're praying. I think they're praying. Good.
As a chemist, what is your feeling about molecular electronics?
As a chemist, what is your feeling about molecular electronics?
Oh, molecular electronics? Of course, that's one of the very exciting domains of nanoscience today. So, as a chemist, I naturally think molecules are the best thing ever invented. There's such an incredible variety of things you can do with molecules. So it's not at all surprising to me that new realms are found for them. You may be thinking of the possibility of improving computing all the way down to the level of a single molecule conducting and so on. At Harvard, a younger faculty member, Hung Kung Park, is working among many people in that particular area, and has done. I see, posters nowadays. People like to put these big posters from talks they've given and all. Beautiful posters that he shows molecules between electrodes, single molecules. So, no question, it's a wonderful field.
You say that big molecules, it's a lot, big spectrum, so a lot of phenomena happens. So if you do this for computing, can you expect something? Is it realistic?
Well, actually, no question, there's great possibilities for molecules of all sizes, probably, but you must be familiar with work that has shown the possibility of using DNA to store information. Enormous. I mean, so whether it actually turns out to be practical in a commercial sense, not clear yet, but it is enormous. I mean, and if it would turn out to be something that is feasible or something like that, it would be poetic, because what I also often think of, in the middle of the 20th century, two things happened within 5 years that have a profound impact, and yet they have a relationship that most people don't think about. 1948, Bell Labs, the invention of the transistor is announced. Well, that's sort of the beginning of what turned into the great explosion of the computer age, you know, digital things and all. And 5 years later, Watson Crick in England announced the structure of DNA. And now, even though more than 50 years, it's gradually becoming general and cultural understanding that, gee, we have computer codes inside us, and they make precisely the proteins that we and our descendants must have to run this complicated biochemical machinery. So there's this connection between computers and us. That's a new idea. You never had that before. People didn't think of themselves as connected to computers at all until then. And now, of course, our kids grow up, you know, from infancy. So they have a much more direct connection to computers all the time. So I really hope I get observed long enough in the next few years to see how this evolves. Your generation, I can well imagine. I can even imagine situations where people graft in some extra memory or extra brain capacity. Who knows? Just a convenient way to do it. I wouldn't be surprised. At any rate, there are just awesome possibilities. When you look back and see over time what has developed, you know, from the orchards I grew up in into what Silicon Valley and all is going on, it's just awesome to imagine what's likely to happen in your generation. So.
I really appreciate that you are transmitting here lots of optimism in terms of science, right? Mm-hmm. But I don't want to be pessimistic, but you compared the other day, last night, I mean, that science as a basketball game, like a guy throwing a basketball into the basket, that you have lots of time, that it's a matter of time when you will score, right? But this is true as long as you have a grant somehow, right? Or you have some funding. What I mean is that science needs money as well, right?
Yeah.
So needs investment. And I think that here in general, in society, if you ask about science, the general point of view is that, science is very interesting. But if you would ask them to make a list of where they would put money in, I guess science is in the last step of the ladder.
Last,
or I don't know, but not in the top, let's say.
Mm-hmm.
That's my opinion, maybe. So I think we still, scientists, need to do a lot of work to convince people that the investment in science is very important. So do you have any idea in terms of that, how we can really convince society, or what scientists can do in this?
Well, maybe what you want to do is become an economist right away. Everybody pays such big attention to predictions by economists, even though they often are very different, and maybe you have 10 opinions of 10 economists, and all 10 are wrong, and so on. It's really striking. But it seems to me, if you are or were an economist and you want to look into the question of what investment in science does compared with other kind of investments, this has been done in particular by Robert Sholow, a Nobel laureate economist at MIT, and there's just no comparison. I mean, science is tremendous. The investment return you get per dollar. So if you're concerned about job creation, which is ultimately really the question, I think the chances are good that even in rather short term, the case can be made that investment in science is very good. I mean, when you look at, say, the laser, it's a tremendous thing. I don't know how to do the calculation, but if you become an economist, I presume you can, and whether I should believe what you say or not. But I think it must be possible to do some sort of calculation to demonstrate the economic value of the laser. It's pervasive. I mean, you can't buy groceries without going through scanning of grocery thing. You play music with laser. All of this, that not at all what Charles Townes had in mind when he conceived of the first maser, the precursor of the laser and all. So the fact that one new thing can change so much. Look at nano, as I mentioned last night. You never heard any talk about nano stuff at all until post-buckyball. I mean, okay, who would have supported a proposal to launch a whole new industry, exploration, new devices and whatnot, if you do a little more work with supersonic molecular beams? Nobody would imagine. Especially if the point was to test whether you could identify some lines in interstellar space. That was the motivation for looking into carbon vapor, because there's some ideas maybe that was, it turns out it's not right, but it was the motivation. So I think science, sure, the nature of it is you can't predict these big things. And people like to say, yeah, even if the economist predicts something, maybe it's wrong, but money, so maybe it means money will follow that. Scientists said, well, we don't know if you make any money, but you may learn something. Well, usually, if you learn something, it may not be that something, but that something in connection with other somethings that you already know can make a big difference. So, you're right. We have to try to make it more broadly understood that that's the nature of things in science. Your best chance, I think, is just pointing to all the historical examples. And there are a lot of them.
Which are, in your view, the most exciting fields or areas within chemistry, or if you like, the new holy grails in chemistry for the years to come?
Well, I can tell you what the majority of people today would say, and then I'll just give my own view. It's nanoscience and bioscience. The chemistry departments, at least in the United States, have turned into almost entirely people in working in both those domains. And no question, those are terrifically fruitful and areas with great potential, and that's why they're exciting and people are working in them. The field of research using gas phase is regarded as like classical music. It's too simple. It's a thing of historic interest only. While my view is actually that's probably premature. I like to tease people who say, oh, small molecules, no interest. Small molecules, you have to have big molecules. And I say, no, wait a minute. Haven't I heard something about nitric oxide? You know, that's a nitrogen and an oxygen. Doesn't that turn out to be pretty important in biology? You know what I'm referring to? It was discovered that in a rather function that a lot of people, especially male people, are interested in, NO has an important role. I want to be very delicate in speaking here. So that's one example. But then I also asked, now what about this story of buckyball? Where was buckyball discovered? Well, there's a nice story. Orville Chapman, a very good organic chemist at UCLA, recognized that buckyball was a very stable organic, or should be a very stable organic molecule. So he set out to synthesize it by traditional method. He spent 6 years. He didn't succeed in making it. And after that, it was discovered in a molecular beam, because in molecular beam, the supersonic expansion business that was used to make it, making carbon vapor expand into vacuum under conditions where the relative motion is very low in the molecules. So I like to say most of chemistry, is free energy dominated. You have enthalpy change minus temperature times entropy change. Well, to make something that has 60 atoms, carbon atoms, is very bad entropy-wise. But if you can drop the temperature term very low, which is what happens in supersonic expansion, then you forget it. You can say, gee, thermodynamics is so much more simpler. We can ignore the second law of thermodynamics. That is the entropy part. And now it's only the enthalpy. So that's why you can make carbon-60 in a supersonic expansion. And it has a lot to do with why you can't make it, apparently, in the traditional way, because almost all chemistry, including what Orville Chapman was doing, is done near thermodynamic equilibrium conditions, because you have all these things colliding all the time. So what I'm saying is buckyball tells you, the story of buckyball tells you that there must be an awful lot of stable chemical species that you don't succeed in making by traditional ways. That almost all chemistry is just a limiting case so far, near equilibrium species. So the whole world of non-equilibrium phenomena, if you do it fast enough, we did some simple experiments to show this. If you expand, say, ethane, 2 carbon atoms, through a supersonic nozzle made of a catalytic metal, it comes out so fast that the traditional definition of a catalyst must be wrong. The traditional textbook definition is a catalyst is something that speeds the attainment of equilibrium, because it usually speeds up both forward and backward reactions, so that gives you the equilibrium. But if you expand so fast you can't do it, what you find is all the intermediates that ordinarily would eat up each other and reach the equilibrium product don't have a chance to disappear in the scene. So what we found was just one expansion. We made 45% benzene, a whole bunch of higher hydrogen, up to 12 to 15 to 18 carbon atoms easily in this catalytic thing. Well, that's just one more simple example of how, if you do non-equilibrium things, you can do all kinds of chem. So this gas phase, obsolete, no interest, lunatic fringe nowadays, waiting, I would say, for some young person to carry further, because I'm convinced you could do a lot more with this and relatively simple apparatus and so on. Another field that is underpopulated, but I think of naturally powerful, is high-pressure chemical physics. When you squeeze molecules together, the overlap of the electron clouds produces great repulsive forces. It has the effect of weakening chemical bonds. And that means you can get new phases, new species, and so on. So it's sort of an automatic catalyst, universal catalyst, high pressure. And again, there's lots of interesting things that point to how much you can do with that, and very little has really been done in the direction of chemical synthesis that could be done. So those are two areas that are, as I say, very underpopulated. I always point out to my students that you want to pick a field that appeals to you intuitively in terms of your temperament, the kind of taste you find you have, not just talent. I think that's equally important. And you look around for things like this that fall between. In a forest, you have big trees that cast a lot of shadow, and you don't find little trees growing in the shadow. They're out in the edges where the shadows of the big trees don't completely overlap. And so it is, if you're a young person looking for an exciting frontier of research, look in the edges of other fields, and maybe between two you find a nice warm little spot in the woods where you can plant your tree and grow your forest eventually.
Okay, we have time for one more question. If not, I would like to, in spite of time flies, we have been here for 1 hour. It has been almost 5 minutes for me. But I would like to especially thank Dudley Herschbach for all his kindness, his brilliancy, his warmship, and also, since Professor Cosio is here, to thank Ikerbasc, because Professor Herschbach is here in a program of Ikerbasc to precisely contribute, in part, not only for that from what you wanted, no? To make science known, and to make science is part of culture, is part of wonder, but also it is a key thing for economic development, for what he said, and in addition for the persons we train that will be good for doing science or for doing anything else because of the brains they develop. And this program is contributing to that, so I specifically want to thank Ikerbasc for this program with the advice of Hakiunde, the Academy of Arts, Science and Letters. And of course, thank all of you for your assistance and for your help all over these years, not only doing your work, but coming to all our meetings with such enthusiasm and happy faces. So thank you very much to everybody. Very beautiful meeting.